All right, so in 10.3, we were looking at polar coordinates and kind of familiarizing ourselves with working with points, plotting them, equations in polar form. What are some polar curves that come up? And all of that stuff is review. It's all stuff you should have talked about in a trigonometry class. Here's where we get into new material. It's how to do calculus with polar curves or with functions that are given in polar coordinates. So kind of like we did with the parametric equations, we're going to be looking at some different circumstances, or some different applications rather. Specifically, we want to be able to compute areas of regions. We want to be able to find arc length, and then we also want to find tangents. So those three things are what we're looking at. And in this case, we're always considering curves that are given by a function of the form r equals f of theta. And to begin with, for areas, suppose we have that function r equals f of theta, and what we want to do is find the area of the region bounded by that curve and the lines theta equals a and theta equals b. We have an image down here that I'm going to show you in just a moment. But as a quick little disclaimer before we get into it, you have to remember a certain formula from geometry. If you have a sector of a circle of radius r subtended by an angle theta, the area of that sector is 1/2 r squared theta. Okay, that's easily derived in a trigonometry or a geometry class. We're not going to derive it here. We're just going to use it. A quick note, though, this formula only works if theta is interpreted as radians, not degrees. So this is assuming theta is in radians. Okay, all right. Let's go to the type of problem we're trying to solve here. So suppose I have some region, and then it's bounded by a curve given in polar form, r equals f of theta, so something like this, and bounded by the lines theta equals a and theta equals b. So you can see what that region kind of looks like here. How do we go about finding the area of this region? Well, what we're going to do is we're going to take the interval AB, which determines the set of all possible thetas for all of the points in this region. Notice if I pick some point arbitrarily in here, then its theta, when I represent that point in polar coordinates, has to be somewhere between A and B. So that's what this interval represents, all the possible theta values for all the points in this region. What I'm going to do is take that interval and partition it up into a bunch of subintervals, the way that we do when we come up with integrals for things. So those intervals will be equally spaced. The width of any one subinterval after doing that will be delta theta. And I'm going to say, let's let the endpoints of those intervals be theta naught, theta 1, theta 2, all the way up through theta n. This will create n subintervals. Okay. Now what I'm going to do is think about what that would look like. So if I set theta equal to theta naught, or theta equal to theta 1, or theta equal to theta 2, we know from the previous section that equations of that form, theta equals a constant, gives us rays or lines through the origin. So what it's doing is it's taking this region and cutting it up into these little pieces the way that you see it here. What we're going to do is try to approximate the area of each one of these little subregions and then add them up to approximate the area of the entire region itself. Now, each of these little regions is close to a sector of a circle. So we're going to use that area formula for the sector of a circle that we showed up above to approximate this. And the way that we do that was we look at any one of these subintervals. Let's say the ith subinterval. So that would be theta I minus 1 to theta I. We're going to pick some sample point in that subinterval, so theta I star. It lives in here somewhere. Plug that into our function, and it'll take us to a point on the curve. Okay? I'm going to treat that point right there as the radius of the circle that this sector came from. This blue region is not a triangle, it's a sector. It's hard to see it, but this is curved right here. Okay, so the radius of that would be f of theta I star, because we have r equals f of theta. That's where we get our r's from. And then theta, the angle that is subtending this arc, is delta theta, because that's the width of that subinterval. That's how we come up with those. So what is the area of this sector that I'm using for approximation here? I'll have that on the next page. There we go. Using that area formula for a sector, it's 1/2 r squared delta theta. But remember, r is f of theta star, or theta I star. Okay, that's the area for just that one sector that we showed on the previous page. But the goal is to sum all of those up, to add up all of those approximations. And like you would expect with a Riemann sum, which is what this is turning into, if we take the limit as the number of those sectors goes to infinity, then our approximation becomes exact. So we're looking at this, the limit as n goes to infinity of this sum right here, where this is the area of each of those sectors. This limit turns that Riemann sum into an integral, and here's what the integral looks like. The integral from a to b of 1/2 times f of theta, there's a parenthesis missing right there, squared d theta. If you prefer to think of f of theta as just r, because remember, that's where the curve came from, r equals f of theta, then you can swap the f of theta out for an r for, just the purposes of making that easier to remember. Okay, let's try doing one of these. I want to sketch the curve r equals 2 plus 2 cosine of theta, and then determine the area it encloses. So if I go back to my notes from the previous section, see if I could find those. The very last page, we gave a catalog of polar curves. So that was right here. We are seeing something of the form r equals a plus b cosine of theta. It was cosine of theta for this one, I think, right? Yeah. Okay. Not only that, a and b are equal to each other in this example. A and b are both equal to 2 in the example I'm looking at. That tells me that I'm looking at a cardioid. The fact that I have a positive 2 in front of that cosine and a cosine itself instead of a sine means this is a cardioid that's not going to be oriented up like this one, but to the right. So I'm going to sketch that thing here. And I'm not really going to worry about being too accurate with my sketch because I'm just getting a general idea of what it looks like. Other problems I might want to be a little bit more accurate, but in this one, that's about as good as I wanted to get. Notice I'm not even labeling anything, I'm just getting a general idea. Okay, now the area it encloses is all of this. I want the area of that thing. How do I get the area of that thing? Well, to graph this entire cardioid, we have to plug in values of theta going from 0 all the way to 2 pi. It makes a full circle and comes back to where we started from if we do that. So the interval for my theta that I want to use here is 0 to 2 pi. Okay? So using this formula then, the area is equal to the integral from 0 to 2 pi of 1/2 times r squared. But this is what r looks like. 2 plus 2 cosine of theta all squared d theta. Now I'm going to do a few things here in one step. So I can factor a 2 out of both of these terms, but remember I'm squaring it. So when I square that 2, it comes out as a 4. That 4 will multiply to this 1/2, giving me a 2. And as a constant, I can bring it all the way out of my integral. So I get 2, integral from 0 to 2 pi. And then what would be left in here is 1 plus cosine of theta, which when I square that gives me 1 plus 2 cosine of theta plus cosine squared of theta d theta. Okay? Now, this cosine squared right here, I can deal with this by using a power reduction formula. So this becomes 2 times the integral from 0 to 2 pi of 1 plus 2 cosine of theta. And then remember, cosine squared is the same as 1/2 times cosine of 2 theta plus 1. Okay? Now I'm seeing that 1/2 in here, and I'm thinking to myself, if I can avoid it, I'm going to try not to deal with any fractions. So I think this might be a good time to multiply this 2 back in, because that 2 will get rid of that 1/2 for me. Let's do that. 0 to 2 pi. That would become a 2. This will become a 4 cosine of theta, and the 1/2 is gone now, so now I have plus cosine of 2 theta plus 1 right there. And this would just give me this. 3 plus 4 cosine of theta plus cosine of 2 theta. Now this is not hard to integrate, of course, but there's a cool shortcut you can use, which is very useful for integrals like this one. And a lot of integrals you'll actually encounter in Calculus 3. This kind of thing happens a lot. So notice that I have cosine functions here. If you think about the function like 4 cosine of x, it looks like this, right? That's 4, that's -4. And if I'm going from 0 to 2 pi, that completes one full cycle of that function, right? The integral from 0 to 2 pi of 4 cosine of theta is interpreted as the area between this curve and the x-axis. But because of the symmetry that occurs in this function, I have the same amount of positive area here as I do negative area here, which means that integral is going to come out to 0. The positive and the negative cancel. So this term right here is going to go to 0 when I do that integral. It turns out that this one is also going to go to 0. Now the reason for that is because the period of this function is just pi. The period of the cosine function is 2 pi, but then if I multiply this theta here by a 2, I would do 2 pi divided by that 2 to give me the new period. So this one, if I'm going from 0 to 2 pi, is going to look like this. It completes 2 cycles. But I still have the same kind of symmetry. See that? This will cancel with this, and this will cancel with these two put together. So this still goes to 0, right? I can do that without having to do any antiderivatives. All that's left in here is 3. So I'm left with 3 theta after integrating from 0 to 2 pi, which of course would just be 3 times 2 pi, or 6 pi. All right. Not bad, right? That's not bad. Okay. Let's move on to another example. This one is harder to do. So I want to find the area of the region inside r equals 1 plus cosine of theta, but outside r equals 2 minus cosine of theta. So again, I need to know what these graphs look like. The first one is another cardioid. In the previous problem, we did r equals 2 plus 2 cosine of theta. But there's like a 1 in front of that cosine right there, which is equal to this one here. That's the conditions that we need for a cardioid. So we're going to get a cardioid that is also oriented like this, okay? Then I also have 2 minus cosine of theta. So the fact that it's a cosine means it's oriented horizontally, either to the right or to the left. The fact that this is a negative means that it's actually oriented to the left. And then we think of this as the A and the B in that catalog of functions. So coming back over here, A would be like a 2, B would be like a 1. So in this case, A is equal to 2 times B, right? So we're looking at a convex limacon. It's oriented this way, which means the larger part of it's kind of pointing that direction. Now, it looks like a circle the way that I'm drawing it, but remember, it's not technically a circle. So we're asked for the area inside this cardioid, but outside this convex limacon, which means we're looking at something like this. Okay? How do I find that? Well, notice, first of all, that these two curves intersect at these 2 points, which I did not draw very well, but, you know, there's intersections there, right? Secondly, notice that both of these curves are symmetric about the about the polar axis. What that's useful for is I can simplify this problem by only worrying about the area of the top half of this region, because then I can double it to get the area of the whole thing. So if I can figure out this point of intersection, then notice that if I applied my area formula with that integral to the region that this is inside, that's the cardioid, that would give me too much area, because that area formula would also account for all of this here, right? It would give me all of this. But then I can compute the area from here to here that's just inside this convex limacon and subtract it to remove this part of the region. So that's what I'm going to do. In order to set up limits of integration, though, I need to know what this point is. So because it's an intersection of 2 points, I can set these expressions equal to each other. 1 plus cosine of theta equals 2 minus cosine of theta. Or 2 cosine of theta equals 1. Or cosine of theta equals 1/2. Now that, of course, means that theta has a couple of solutions within one revolution of the unit circle. So cosine of theta equals 1/2 at pi over 3 for one of those locations, and then also 5 pi over 3. This right here corresponds to theta equals pi over 3, whereas this right here corresponds to when theta is equal to 5 pi over 3. However, because we're going to simplify our approach to this problem, we're not going to need that one. We're only going to need this one. So what I'm going to do is I'm going to start by finding the area of the cardioid from theta equals 0 to pi over 3. And that's found by doing 1/2 r squared. Remember, this is what r is in this case. 1 plus cosine of theta squared d theta. And then I'm going to subtract from that the area, still from 0 to pi over 3, of this convex limacon here. So that's going to look like 2 minus, need my 1/2 there, 2 minus cosine of theta squared d theta. Okay? Now I can do a couple of things to simplify some of my work here. First of all, even though I have 2 integrals, I can consolidate that into one because I have the same limits of integration here as I do here. So I can just consolidate all of these by subtracting the integrands. I can also pull a 1/2 out of everything. So that's going to become a 1/2 integral from 0 to pi over 3. Let's go one step further and actually square these things. So if I were to square this guy, I would get 1 plus 2 cosine of theta plus cosine squared of theta. And then if I were to expand this out, remembering that I'm subtracting all of those terms, 2 squared is 4, but it's going to become a minus 4. Then when I multiply this, I'm going to get negative 4 cosine of theta, but then I'll distribute that minus and make it plus 4 cosine of theta. And then finally, I'm going to get a cosine squared, but it's going to become negative here. Minus cosine squared of theta d theta. All right? What now? 1/2, 0 to pi over 3. I have a cosine squared and a negative cosine out of squared. Those cancel. I have 2 cosine of theta plus 4 cosine of theta, so I should have 6 cosine of theta here, and then 1 minus 4, I should have minus 3 d theta. I can even go one step further and factor a 3 out of this, so I would call that 3/2. When I integrate, I'd be left with 2 cosine of theta here, which becomes 2 sine of theta. This would have been a minus 1, so I get minus theta from 0 to pi over 3. Now, when I plug a 0 into either of these thetas, these both go to 0. So plugging a 0 in doesn't contribute anything. Let's just worry about the pi over 3. I'm going to have 3/2 times sine of pi over 3 is root 3 over 2, but then I'm going to multiply it by a 2 and just end up with a root 3. And then here, I'm going to get just a pi over 3, minus pi over 3. Okay, and that is my answer. If I wanted to, I could distribute some stuff. I'm just realizing now, oh, no, this is fine. So yeah, I can leave my answer in this form, or I can distribute the 3/2 in, or whatever I want to do with that. But that's basically the gist of it. Cool. All right, I'm going to make sure I'm not forgetting anything important. For some reason, I feel like I'm forgetting something important. Nope, I think it's okay. All right, so that's going to be it for that video. In the next video, we're going to take a look at arc length.